Hello, my name is Gareth Tribello and I'm a Senior Lecturer in Maths and Physics at Queen's University Belfast. I don't just do mathematics all day though. In my free time I play clarinet in a wind band that is based in Dundonald. In the last few months the conductor of this wind band has taken to saying that when there is a crescendo in the music, the volume we play at should increase exponentially. This irritates me immensely as it makes no sense. It is a mathematical nonsense, and in this video I'm going to explain why. So if I have your attention, Paul, let's begin. So here is a piece of music that contains the instruction to crescendo. Instruction to crescendo is indicated in red. What we are looking at is the isosceles triangle on its side that has no bass. It is this marking that tells the players to get progressively louder and louder, in this case from moderately loud, mezzo forte, MF, to loud, forte, F. Mathematically, we would say that the width of an isosceles triangle like this one increases linearly as we move from left to right in the direction indicated by the arrow. To understand the difference between linear and exponential growth, let's recreate the linear growth of our crescendo in a different form. I have knitted this piece of material so that the number of stitches in each row grows linearly. You can see that I have a little isosceles triangle of cloth that looks like the crescendo sign. Furthermore, the widest point in my triangle is about as long as my thumb. Let's now see how much longer the base of the triangle is if we grow the number of stitches exponentially instead of linearly. Phew. We now might ask, why is the exponential so much wider? You can understand this if I explain how I created linear and exponential growth in my swatches. To grow the number of stitches linearly, what you do is you knit across the row like this. When you get to this last stitch, you do what's called a knit front and back. And what you can see is that when you come to start the next row, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9 stitches, rather than 8. For the exponential growth, what you do is you knit front and back into every single stitch, like this. So you can see, although we had 8 stitches when we started this row, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've doubled the number of stitches. Let's now consider how the number of stitches will change as we move through the rows if we have linear and exponential growth. For linear growth, if we start with 1 stitch, then we add 1 stitch in going from row to 1 to 2. We will thus have 2 stitches in the second row. When we knit that row, we add a further stitch so that we will have 3 stitches in the third row. We then add 1 additional stitch when we knit this new row so that we'll have 4 stitches in the fourth row. If we continue this process of adding 1 stitch per row, you will see that we have 5 stitches in the 5th row, 6th in the 6th, and so on. For the exponential growth, remember that we knit front and back into every stitch. In going from row 1 to the next row, we thus double the number of stitches. If we start off with only 1 stitch, we will have 2 stitches on the second row, 4 on the third, 8 on the fourth, and a whopping 16 stitches by the 5th row. If you remember that the 5th row of our linearly growing swatch only had 5 stitches as opposed to the whopping 16 stitches in our exponentially growing one, you can start to see how much faster exponential growth is than linear growth. Now a small confession. When I imagined this video before doing any of the knitting, I never thought that the exponentially growing swatch would look like this crinkly mess. I thought I would be able to lay the cloth down flat like the linear swatch, say, look at how massive it is, and say, you see, Paul. The reason that I thought this was because I thought about things in terms of the flat diagrams that I showed on the slides. I forgot that my swatches would be three-dimensional and not two-dimensional. In fact, when you look at the linearly growing swatch, you can see that even this is curved. We can understand why the cloth is curved by thinking about what is going on in 3 dimensions by you looking at these blocks. Remember that each stitch has a constant width. When I increase the number of stitches from 1 to 2, I thus have to squeeze 2 stitches into the space that was previously occupied by a single stitch. I thus cannot pile directly on top of each other like this. Instead, I need to curve the blocks around like this. If you do this fitting of stitches into the space of the previous row, you get a curved wall of blocks something like this if the width of the blocks increases linearly. If, by contrast, you increase the number of blocks exponentially, you get the crinkly pattern that we saw in the knitting, as you can see here. Even more interestingly, to fully understand this crinkly shape, we need to engage with a much more obscure area of maths called non-Euclidean geometry. This topic is much less everyday for mathematicians than the linear and exponential growth that I have talked about thus far. Non-Euclidean geometry is something that I certainly never imagined I would end up talking about when I set out to make this video. I mention this because I think there is an important lesson there to finish off this story. If you engage with maths creatively, as I have here, you almost always end up finding out something new, which is the fun part. Maths is not just about memorizing equations. Maths is a tool that good mathematicians use to learn about the world around them.